Vanakkam. Welcome to this video on biomechanics. In this video, we will be introducing some basic principles, basic terminologies, basic principles of gait analysis. This is a topic that I wanted to discuss in much greater detail, but due to unavailability of time, we are only able to discuss whatever we are now going to discuss because of lack of time and because of the greater emphasis that we placed on other topics which are also equally important, like how do you measure kinematics using IMU, some practical examples. These are topics, research level topics that students can take and perhaps implement in their own work, their own research. So, as we expanded more on that, this topic has become squeezed because there is very little time available. Alright, with whatever time that is available to us, let us proceed. So, in this video, we will be discussing stability and the various phases of gait or walking, gait cycle, and specific terminology related to gait. When you say stability, what do you mean by stability? So, what is meant here is the criterion for overall stability. So, there are, it turns out, different levels or different specific definitions of stability. Here we are discussing mechanical stability, the stability of the person who is standing. Suppose a person is standing with two legs like this. The criterion for stability is that that the center of mass lies between or lies somewhere within the area that is completely spanned by the 2 feet. So, something to keep in mind, something that you can also watch for is that as people get older or if there are some pathologies, you will see an adaptive mechanism used by individuals to overcome lack of stability. It's a common mechanism, global adaptation to any pathology or any deficit, right? That is to increase the distance between the two legs so that or have a very broad span. That way, even if you slightly move away, what will happen is that they will not fall. So, this is a strategy. This is something that even healthy people, healthy young adults will use in uncertain situations. For example, if there is a slippery space, that is if they have to walk on some, say, a corridor that has some oil spilled, even we will use a broader span so that we will not fall. This is not something that we do consciously, because walking is something that we are doing since a very young age, and adaptation to this is also something that we have probably learned from a very young age, and we have been doing millions of steps since a young age, and probably this is not something that is consciously perceived, but this is something that we will do. So, whenever there is an uncertain situation, people will naturally start taking steps that are farther away, side by side, that is mediolateral distance between the two legs increases. Of course, that will result in slowed performance, but the idea here is to improve stability over performance. Whenever it is a competition between stability and other metrics of performance, stability trumps everything else, because falling down has a huge consequence. There is a huge cost to falling down. Older adults, people with pathologies, when they fall down, there is a high probability that they will develop, or there is at least a higher probability that they will develop injuries or disorders that could lead to hospitalization or even death. So, it is very important for people to not fall down, especially older people. If they fall down, there is a high probability that they may not recover. This is a function of age. So, there are many aspects of this stability that comes into the picture. So, remember, students of biomechanics, if you are having someone older, be your parent or maybe a grandfather or a grandmother, a grandparent, something that you need to emphasize is that they don't fall down. You need to emphasize, you need to create an environment in which there are less hazards in their household, in the household or in the space in which they are living, so that there is a lower risk of falling for older adults. Also remember that older adults may have other problems. We discussed these earlier. For example, women may have osteoporosis. So, the probability that they will recover from a fracture is much lower when compared with young healthy adults. So, there are many aspects of this. So, coming back to the topic of stability, stability essentially implies that the center of mass should be over the spanned area, and remember this stability is different from what are broadly called as stable movements, or what are broadly called as balance. So, how is this stability related to balance itself, or the sense of balance, or maintenance of balance? These are not necessarily the same topic. Okay, mechanical stability is what we are discussing. It does relate to balance, but it is not a synonym for balance. So, these are different. So, how does this stability work? Because during upright standing, the right foot causes torque in one direction, the left foot causes torque in the opposite direction, and because the net torque on the human body is the sum of these two torques, it will almost sum to 0, but moment to moment or instant to instant this will likely not be the case. That is why whenever you say quiet standing, it is not like you are standing absolutely quietly. There is an amount of fluctuation that happens. So, when I am standing quietly, there is always a little bit of sway. This is body sway, this is normal, this is not unhealthy, this is called normal body sway. Also, something to keep in mind is this body sway varies as a function of age, pathology. Also, whether your eyes are closed or open will determine how much sway you are having. This sway that happens in these two directions, called mediolateral sway. If it is happening in these two directions, anterior posterior direction, right, but sway happens in both of these directions. So, it does not have to restrict itself to either the mediolateral or the anterior posterior, it can happen in any of these directions. So, as you close the eyes, the sway tends to increase. That is another thing. So, whenever you say that these two torques are cancelling each other, so there is an amount of complete balance, but that is not exactly true. That if that happens, then there will be no sway. So, instant to instant small amount of sway or small amount of slight imbalance is there, but that is immediately corrected. So, there is an amount of correction online, feed forward or feedback based correction that appears to happen, that ensures this stability. Okay. Let us not go into much detail into how this happens, that is beyond the scope of this course and this lecture, but it appears like there is a kind of active control over this. And there are many hypotheses that relate to these kind of topics. Please check these, those who are interested. Of course, if someone is pushing you to the left, and the center of mass is away, then there is a probability that the person will fall down, or if it is on the right side, then the person will fall down on the other side, right. If the torques cannot balance in either case, and if the foot is not able to offer the right amount of friction and the other type of forces that will overcome this kind of instability in an instantaneous manner, there is a likelihood that the person will fall, and we do fall down. I mean, healthy humans, healthy young adults also fall down. It is not like we do not fall down. but there is a higher incidence of falling in older adults and in people with motor disorders. More than that, there is a higher incidence of fear of falling. There is falling and then there is fear of falling. The apprehension that you are going to fall is a problem. Older adults have this problem that they might fall, and so they use adaptive mechanisms to overcome this fear. There is a difference between an actual problem and a fear. A fear is a perceived problem, is it not? So, something to keep in mind. So, how is stability achieved? Okay. If there is stability of the biped, of the human who is standing with two legs, this overall stability presumes stability locally at the many joints that are formed by this, no? Local stability. Right. A particularly interesting or good example of good design is the knee joint. Remember, long time ago, one of the early weeks we discussed the knee joint, and when we discussed the knee joint, we discussed the ligaments that form the knee joint. You know, what is the purpose of these ligaments? There are two collateral ligaments and two cruciate ligaments. By now you should remember this. If not, I request you to pause this video, open a new tab and check out the knee videos. We have discussed the knee ligaments in much greater detail there. This collateral ligaments, collateral ligaments means co-lateral. Co means these ligaments are on the same side, collateral means same side. So, they connect to the same side, right, collateral ligaments, and then cruciate ligaments, ligaments that cross over. Cruciate means crossing ligaments. Crossing ligament on the back side is called as the posterior cruciate ligament, and crossing ligament on the front side is called as the anterior cruciate ligament. And when we discuss these ligaments, we mentioned an important role, a critical role of these ligaments is to provide stability. Right. Of course, stability, there is also contribution to this knee stability by oblique ligaments and patella. So, there are actually 6 ligaments. So, there are not just these, there are also other things that come into the picture, but the point is that it is a design that allows for a great amount of articulation in the form of knee flexion, and yet it provides the stability. Consider that this is a joint that is going to take a huge load and provides for a great amount of flexibility, or rather articulation movements, in at least in the flexion direction. Of course, there is not a sideways movement, but that is not the purpose of the knee joint. Despite all these constraints, it is also built with a great amount of stability. This is a particularly great example of good design, something that we have discussed in reasonable detail when we discuss the knee joint, remember. So, please do check that out. So, this stability in the knee joint contributes to the overall stability, but remember, it is not just the knee joint. There is stability at the hip joint, there is stability at the knee joint, and there is stability at the ankle joint. All this stability together leads to the overall stability. Also, what else might affect stability? Let us say that you are carrying a weight. I am carrying a weight on the side, for example. If the person is not carrying a weight, the center of mass is going to be somewhere here for this person. If she is carrying a weight on the side, the center of mass is shifted, right. If you are doing this occasionally, it does not really matter. You might be able to generate compensatory torques on the other side of the body so that you do not fall. It is something that you do once in a while, and you probably can develop compensatory mechanisms or adaptive mechanisms for the time being, for the few times that you are doing. right. So, when you are lifting this weight, the center of mass shifts outside, right, at least momentarily. So, there is an amount of instability that this person undergoes, right. So, there is a need to compensate. So, there is contortion of the position to compensate, right. If this is done once in a while, it does not really matter, but if this is your job, this is something that you do regularly and this is something that you keep on doing, what happens is that if this is something that you keep doing a lot of times every day, then what happens is that there is a possibility of development of some musculoskeletal disorders, muscle strain, back pain and other such things. Also, something to remember as we are discussing this, people with a belly, people who have big bellies, this is a relatively common problem nowadays, because obesity is the latest syndrome, is the latest epidemic that we are all facing, big bellies. What this does is that it moves the center of mass little bit further in the anterior direction, right. This leads to a situation in which there has to be a development of compensatory torque in the posterior direction. In the sagittal plane, you will have to develop compensatory torques in the opposite direction, and because these people will have to continuously, as long as they are standing and as long as they are walking, they will have to consistently and continuously develop these compensatory torques with the muscles of the back, erector spinae, whatever these muscles are. There is a high probability that the muscles in the back and the bone and the spinal cord, the vertebral column will take a huge hit. That's why these people end up having other musculoskeletal problems. So, it is very important to keep a healthy physique, in particular to avoid this big belly. If you have a big belly, there is a higher probability that you will develop as a side effect, there will also be this development of these musculoskeletal disorders. Another example is pregnant women. For example, pregnant women, the same thing happens. So, there is a higher weight on the front side, just 2-3 kgs, no, baby at in the third trimester, about 2.5 kgs, 2.5 kgs, 3 kgs for example, 3 kg load, but this is something that they carry throughout, right, every moment until the baby is born. This tends to cause a tremendous amount of back pain to this person, to these ladies, right. So, something that others cannot easily understand or perceive, but people with big bellies can understand what this means. So, how are these arising? As compensatory mechanisms. So, these compensations can lead to other unwanted musculoskeletal problems. Here when you are lifting a weight in an uncomfortable position, compensatory mechanisms lead to a situation or lead to development of musculoskeletal disorders, right, or poor ergonomics, poor workplace ergonomics, mechanics, right. Now, imagine a person is weighing 700 newtons, a little more than 70 kg. Remember, 70 kg is not 700 newton, because 70 kg in newton with G equal to 9.81 will be slightly less than 700 newton, but here we are discussing about a person who is 700 newtons and the weight is supported by the 2 foot, and the cross sectional area of both feet, how much would that be? We do not know, right. That obviously varies as a function of your shoe size or your foot size, but you can compute that. What you can do is, you can take an A4 sheet, and draw an outline of your foot, okay, and or maybe you can do something else. You can use a graph sheet and draw an outline of your foot and compute what is the area of your foot. Of course, if you want to buy footwear, You would do something like this. If you want someone else to buy the footwear for you, you will draw this outline and then send it with them and they will buy it for you. Happens in childhood for children. This is something that is done. A question is, what is the cross sectional area of your foot? Compute that. It varies between people, of course it varies between people. Some people have large feet, some people have small feet. So, the total cross sectional area of both the feet put together for an average person, for a medium person, is about 350 square centimeter. Now, a question is this entire 350 square centimeter in touch with the ground? The answer is no, because it is usually the ball of the foot and the heel of the foot that is in touch, but there is an arch in the middle of the foot that is usually not in touch with the ground. Okay. So, the entire area is not in contact with the ground. Okay. After accounting for all the area that is in contact and all the area that is not in contact, you will realize the average pressure, of course this will vary as a function of time. This will vary depending on whether you are shifting the weight from one foot to the other foot, something that we do all the time. You may not realize when you are standing for a long time, you might shift like this. Now I am shifting most of my weight to the right side. When I am doing that, for example, I am shifting most of my weight to the left side. This is something that we do not at a conscious level, but we do this all the time. Assuming all these things, and adjusting for all these things, on an average, the pressure on each foot, right, is about 10 Newton per centimeter squared, considering only some of the feet or some areas of the feet are in contact with the ground, right. While walking, what happens is, there are phases of walking during which the entire foot, even otherwise the entire foot is not in contact, but there are phases of walking during which only part of those parts that are in contact are in contact. That is, earlier when you are simply standing or when you are quietly standing, both the ball of the foot and the heel of the foot are in contact. But if you are just lifting your foot, right, if you are lifting your foot, the heel first goes up, right, or there is plantar flexion, right. So, and then the toe leaves, right. So, as you are doing that, the contact with some part of the foot is lost, and while you are striking the ground again with your feet, first contact is established with some part of the feet, not the entire part. So, the forces or the pressure during walking will be much higher, and peak forces can be as high as 60 Newton per square centimeter. So, that is approximately 1 centimeter square, approximately. That is approximately 1 centimeter square, and 60 Newton force is applied on this area. Then you realize this is essentially a very large force. And for balance, what happens is, because there is stability, the ground applies an equal and opposite force on the feet. That is why this whole system is in equilibrium. And this is not a constant. This varies as a function of the amount of force applied by the feet on the ground. And because the amount of force applied by the feet on the ground changes depending on the phase of walking, depending on the speed of walking, depending on a whole bunch of factors, it turns out that the reaction force supplied by the ground on the feet also changes. Okay. So, this is also something that can be plotted, that ground reaction force is also something that we can plot as a function of the phase of walking, as a function of time. And this is something that keeps varying. So, this This diagram represents the ground reaction force vectors, right, at different phases of the walking cycle. Why are these forces in different directions? Isn't it always supposed to be against gravity? No, no, no. These ground reaction forces are reaction forces to the applied load, right. So, this is an indication of the kind of load that is applied on the ground by the feet, right. This is in another way of studying that. So, this represents perhaps what the system, what the movement control system is attempting to achieve during walking. This is one of the ways in which we can understand. There is too much detail that I am not getting into, just touching upon this terminology. Okay. So, what are the various phases of walking? What is this various phases of walking? This is called as Gait cycle. So, if you take two successive occurrence of any of the repetitive events of walking, and that interval and the set of all events, the time interval and the set of all events that happen within the time interval is called as Gait cycle. Okay. That means that I could take this between any of these important or salient events and wait for that salient event to happen again, because it is a cycle. I can analyze it whichever way you want, but for consistency, generally the time between the first heel strike and the next heel strike is considered as one cycle of gait. It need not be just the heel strike, but this is a standard that people use. A lot of literature uses this approach, so we can understand. It's a convention as opposed to a technical requirement. You can take it whichever way you want. You can start it at toe off, for example, no problem. But heel strike is the method that is used by many researchers and used by many papers, much of the literature. Okay. And both the legs go through these phases, right. The stance phase, during which the leg is in contact or the foot is in contact with the ground, and the swing phase, during which the foot is in the air, right. Of course, the specific details or the nomenclature changes across literature, or different researchers use slightly different terminology, but it is useful to understand terminology. So, in general, we can divide the Gait cycle into two broad halves, not necessarily exact halves these, okay. Two parts, we will say, two broad parts. One is stance. This is the time when a foot, a given foot, is in contact with the ground. This is the time between heel strike and toe off of that foot. This is the time when the heel is striking. Heel strike means, now consider my hand as the foot, for example, so that I can explain. And that means this part of the hand that is connected to the wrist is the heel, and this part of the hand that is most distal is the toe, for example. So, this, let us assume that the index middle finger is the big toe, for example. Actually, the thumb is the big toe, but it is far away. So, the hand is different and the leg is different, right. But let us assume that this is the big toe, right. I am keeping like this. When the heel is striking the ground, that is called heel strike, and then the whole foot comes in contact with the ground, and as the other foot has finished its swing phase, this this feet raises, and then there is a toe off that happens, right. There is a toe off that happens. So, this time between the heel strike and toe off and the set of all events that happen during this time together is called as stance phase. Okay. This happens in the following sequence. First, the heel strikes the ground, and then the foot goes flat. This is called a foot flat or the loading phase, and then there is a mid stance phase, and then there is the terminal stance phase followed by a pre-swing phase just before swing, right. Okay. And just and this is called as the stance phase, and swing phase can be divided into two or three distinct phases: the initial swing phase, the mid swing phase, and the final or the terminal swing phase. Okay. So, there is loading, there is mid stance, this is loading is also called as what? Loading is also called as foot flat, terminal swing, and then heel strike, loading or foot flat, mid stance, terminal stance, and then pre-swing, right. And then there is initial swing, mid swing, terminal swing, and then the next heel strike starts. The time and the set of all events between one heel strike and the next heel strike is called as a gait cycle. But I could also study it between one initial swing and the next initial swing, or one toe off and the next toe off, for example. Okay. I could also study it between some other salient part of the cycle and the next occurrence of the same salient part, right. I could do that, but generally we study it between heel strike and heel strike. Okay. So, this phases, the initial swing, mid swing, terminal swing together constitutes the swing phase. Heel strike onwards, heel strike, foot flat, mid stance, terminal stance, and pre-swing together constitutes the stance phase. The way this diagram is drawn, it appears like we spend more time in the stance phase than in the swing phase, and that is actually true. We do spend more time while walking, we do spend more time in the stance phase than in the swing phase. The right leg and the left leg follow the same kind of same series of events, right. So, there is no difference between the right and the left legs, but that does not mean that they both happen at the same time. That is not possible, right, because if one leg is in swing phase, if the other leg is also in the swing phase, that means that both the legs are in air, that means you are like flying or you are jumping. By the way, that is a sport that we do engage in, not walking. During walking, at least one of the foot is in the ground at any given time, and there is also a particular time during which both the feet are in ground. This is called as double support phase. Okay, double support phase. This is the time during which both the feet are in contact with the ground. So, this is the difference between walking and running. During walking, there will be a particular amount of time during which both the feet are in contact with the ground. This is called double support phase. Okay. So, let us take for example, the left leg is undergoing a swing phase. At that time, the right leg is undergoing a stance phase, and that makes sense because the left leg is swinging, is in the air, the right leg is in contact with the ground. And then the left leg, there is a initial contact or the heel strike that happens in the left leg, but the right leg has not yet left the ground. That phase is called as the double support phase, right. And then the right leg starts swinging, right, initial swing. During this time, the left leg is supporting the body, and then the right leg makes an initial contact as a heel strike, and then the double support phase again follows. So, and this continues, right. So, about 60 to 65% of the time we are in stance phase, and about 35-40% of the time we are in swing phase, and there is a small amount of time during which we are in doubly supported with both the legs, right. This of course varies with speed of walking. Of course, fundamental difference between walking and running, because there is a walking race in Olympics and there are running races. What is the walking race supposed to be? You should not ever have a single support walking. Single support walking throughout or disappearance of the double support essentially constitutes running. Walking is a situation in which there is at least some amount of double support phase. Okay. I do not know if you have seen these videos, do check them out when you have time. When you have time, do check them out. Walking, fast walking Olympic events, the way they walk, they tend to move their hips and compensate in such a way that there is always double support, but they tend to walk faster. Check that out, you will understand better what I am saying when you check it out. So, for example, when the right leg is striking the heel, there is toe off here, and then there is foot flat, and then there is toe off, then this follows, this cycle continues. Other things that are of interest are stride length, that is distance between two successive placement of the same foot. So, between one heel strike and the next heel strike of the same foot is called as stride length. For example, here we are considering the left foot, and when the left foot again undergoes a heel strike, this is one heel strike, this is one heel strike for the left foot. Between this, the distance, the total distance that is crossed is called as stride length. Okay. Of course, some part of this would be crossed by the right steps or the right leg step, and some part of it would be crossed by the left leg step. Okay. Step length is the distance moved by a single foot in front of the other one. So, stride length is the total distance crossed by a given foot between two successive heel strikes, for example. But then in the meanwhile, a part of this movement is made by the other foot, right. So, step length indicates distance moved by a given foot, one foot at a time in front of the other one. This is called step length. Okay. Step lengths that are different, is this a sign of pathological gait? Question. No. We need to discuss this. I will come back to this gait analysis or pathological gait simply by using step lengths and stride lengths and times. Okay. Also, sometimes there is a tendency for people to take short step lengths on one side and with single support on the other side. Generally means there are some problems with single support on the other side, and also side to side distances sometimes may vary depending on the particular type of walking that is being used. Some other terms of interest. Cadence is the number of steps that are taken in a given time, say for example in a minute. Or this. Cycle time is a more standard unit, that is 120 divided by the cadence. Speed in meter per second is essentially stride length in meters multiplied by cadence, but then stride length is not a constant, assumed to be a constant, but it need not exactly be a constant. It might vary, it is known to vary. Speed is essentially stride length times cadence divided by 120 or stride length divided by the cycle time. So, these are some other terms that are frequently used in gait literature. Now, let us discuss briefly about how to identify and understand pathological gait by simply understanding stride lengths. Right. So, something to keep in mind is what are some measures of pathology. So, if stride length is always a constant, is it always a constant? Something to ask. It turns out that as people walk with different speeds, people do not walk always with a constant velocity. That is a very artificial construct. People keep changing velocities as they walk. It is very unusual for people to walk with the constant average velocity. That is a very unusual situation. So, people change velocities as they walk, and also it varies on the type of topography or where they are walking, right. That also varies. Maybe it is a slightly hilly area, there is a small hill that they will have to go up, or maybe it is they will have to go down the hill, or maybe it is flat, or maybe it is concrete, or maybe it is tar road, or maybe it is a dirt road. All these things come into the picture. There is plenty of factors, right. So, one thing that is known is obviously straight length varies as a function of speed, that we can expect. So, and speed itself varies as a function of many of these topographical factors. So, there is no single definition of this, but what is known is, do you correct for changes in straight lengths as a function of some goal? Let us say you want to maintain a particular speed, for example. How do you correct for these errors, right? And how does that compare in health and disease, right? People have developed approaches to study this using time series analysis techniques, right. These kind of techniques, although they do not form part of our course, I will just mention this for your knowledge. One of this technique is the so called detrended fluctuation analysis. What this does is it detrends, that is, it removes the trend, removes the mean, and then studies the movements as fluctuations that happen about this mean, and how these fluctuations, are these persistent or are these not persistent. So, essentially what this does require a large amount of data. You need to walk several hundreds of steps, perhaps thousands of steps, for you to get this data, for you to have enough length so you can perform this analysis. There are modified algorithms that provide for performance of this in shorter time series data, but that might be compromised on its interpretation, but that is outside the scope of this discussion. The point is that there are these kind of techniques that are used to study this. So, if there is less persistence or anti-persistence, so there is a tendency for people to correct for errors that happened in the previous stride, right. That is healthy, right. That is something that you do not see in people with some disorders. Do check this, do not believe me, always check everything that I say, right. People have also studied this using other methods of time series analysis. For example, people have used short term Lyapunov exponents. So, people have used this short term Lyapunov exponents to determine how many steps are affected by the current step, or rather the past how many steps are affecting your current step, right. So, there are these kind of time series based analysis that could also help us classify healthy gait and pathological gait. I am not going into the details of these, but do check this out, right. Just by observing walking, just by measuring stride lengths and times, we might be in a position to classify health and disease, and then find a way to treat according to that. So, this is a very brief introduction to gait. So, in this video we looked at what is stability, what constitutes stability is stability in the joint, for example stability in the knee joint, we gave the example of that, and what is a gait cycle and what is the standard way of representing or discussing a gait cycle, and some other terminologies. And we also gave a very brief introduction to some of the analysis techniques that are used to study gait time series approach. Right. With this we come to the end of this video, and with this we come also to the end of this course, right. So, I would like to take the time to mention the availability of another course that is offered by me, which is on neural control of movement, neuroscience of human movement, essentially speaking about the various aspects of the movement control system, various neural aspects, right, brain related control, spinal control, the contribution of basal ganglia and cerebellum, reflexes and voluntary control, various other aspects, neural aspects. So, the course does not assume any knowledge of neuroscience. So, the course begins with the bare basics, bare minimum biology, physics, and the course builds from that basics to an advanced level of discussion, just like this course did. Okay. So, I request you all to seriously consider taking this neuroscience of human movement course in future offerings. So, with this we come to the end of this course. Thank you very much for your attention. Vanakkam and Jai Hind.